Welcome to Intro to Exponential Thinking, Progress at the Edge of Possible, with Aaron Frank, Principal Faculty, Singularity University.
All right. Good afternoon. Wow, it's bright. How are you guys? Coming up on the end of the program, so thank you for spending the last few moments at VRLA with me. It's great to see you. This is my first VRLA, so I just want to thank Cosmo and thank the VRLA team for having me. What I'd like to do in this session is set some context about why is it that we're seeing so much change in the world today. So, a conference like VRLA, we're all here, wowed and surprised by all of these incredible developments happening in virtual reality. We've seen, incredible developments just in the last few years. But if you take a step back and look at what's happening, across the world, especially in technology, we're living in an age of explosive technological development, radical geopolitical upheaval. It's a really uncertain time in our world. And so I'd like to conclude this conference today with a framing talk around how to make sense of why we're seeing so much change. So for an audience like this, I imagine most of you are familiar with who this is. And so regardless of what you think about Palmer Luckey, incredible story. I mean, if you think about what he was able to accomplish. So if any of you not familiar, this is Palmer Luckey. He's the founder and the inventor of the Oculus Rift. And so what you have here is a teenager at the time who was frustrated that the virtual reality headset device that he had access to in his college university research lab, he couldn't also access at home. Only the wealthiest, university research labs had access to a device like, in this case, a virtual reality headset. And so what does he do? He goes to his parents' garage, he takes apart a smartphone, rearranges the components, realizes that it's actually a fairly high-functioning VR headset, puts it on a crowdfunding campaign, raises $2.5 million, 18 months later, sells the company for $2 billion to Facebook. I mean, this is by no means a common story, but something that is becoming incredibly less rare. And so just to signify or signal, this is a story that we're going to see happen more and more. I imagine you're probably less familiar with this person. So this is Jonathan Zornow. So I interviewed him for an article that I wrote last year. Similar to Palmer's, an ordinary individual, worked as a web developer, lives in Seattle, certainly had no background in manufacturing, had no background in robotics, yet somehow he was able to debut this last year, which is, as far as we know, the world's first demonstration of an automated stitching technology, so a robot able to automate the stitching of apparel. So if you want to talk about a disruptive technology, this is an incredible and stunning piece of equipment that has far-reaching implications for millions of low-wage earners, whether it's this specific application or others. The fact that we can now automate the stitching of clothing is incredibly disruptive to the labor market. So how is it that a 20-something-year-old individual in Seattle with no background in any of these technologies was able to do this? So when I interviewed him, he shared with me that the way he came up with this idea is he used to spend his nights falling asleep watching a show on the Science Channel called How It's Made. And the reason was that the repetitive automation, the repetitive machines running in the factories would sort of soothe him, put him to sleep. But in one episode where they showed how they made blue jeans, he was frustrated with this distinct presence of human fingertips in all of the clips. There was still quite a bit of human labor involved. And so when he that evening decided to look into why this was the case, and what he found is that for decades, researchers and roboticists have been trying to automate stitching, but the reason stitching clothes is so challenging is the complexity of working with a fabric that bends and moves. And so robots are really good at working with stiff, rigid things. And so the traditional approach was for roboticists to meet the complexity of working with clothing with equally complex robots. So what Jonathan decides is, well, why don't you just make the clothes stiff? And so in another article he read in Make magazine talking about the water-soluble support structures for 3D printers, was inspired to come up with this chemical compound that washes out in warm water, but would stiffen, in this case, a t-shirt. The other piece of that robot that you saw in the video 10 years ago would have cost millions of dollars, only the wealthiest companies would have had access to, that he was able to rent off the shelf. And so we now live in a world where individuals living in Seattle, web developers who can come up with novel ideas, can not only have the ideas, but then actually do something with it and try and come up with interesting things. So this is a really unique part and era of human history, where we're seeing these types of stories happen more and more. So I'm based at an organization called Singularity University. So we're based at NASA Research Park, and this is really what we look at. We try to understand why is it that we're seeing so much innovation, so much radical change in technology in the world today. And primarily, the core feature of the world that we look at is this idea of exponential growth. This idea of how exponential curves are operating in these technology developments. And so that's really the core of how we think about the world. So let's explore what I mean when I say exponential growth. So we learn about exponentials in high school algebra. We have a vague sense of how they work, but the human mind is actually really poorly equipped to think in an exponential way. What's that? I'm sorry. If you have questions, feel free to shout them out. So when we think about this idea of exponential growth, the human mind is really not equipped to do this well. So as a thought experiment, I'll ask you. So imagine your manager comes into your office, or your boss comes in and asks you to make a decision. So they show you a briefcase, and inside the briefcase they tell you is $1 million, and you can have this right away. You know what $1 million looks like, you know what it feels like. Or alternatively, I'll give you a penny. We'll double the penny every day for a month, and whatever accumulates at the end of that month, you can walk away with. So which is the right decision? Which should you go with the briefcase? You know $1 million. You should go with the penny. Penny. So why the penny? It's more money. How did you make that decision? I imagine you thought about it, right? Yeah. So that's a great point. So you guys are smart. You all know the answer. The penny ends up being more. But here's the problem with the penny. And here's the way you made that decision is you used your intellect and your logic, which is, of course, the right way to do it. The problem is we're emotional creatures. We make emotional decisions. So let's imagine that we choose the penny, and your boss comes in and says, 15 days later, let's check on this penny. Let's see, how is that penny doing? You've turned down the $1 million. We hope this penny is, it's halfway through the month, so we assume you'll be at least at $500,000 by now. That penny has turned into $163. This moment, by the way, this decision is not unlike the decision that strategists, executives, managers at companies are asked to make every single day, that you are likely being asked to make in your decisions if you're building companies. Do you go with a proven technology, or do you bet on some unproven but high potential technology? So halfway through the month, this is alarm bells. This is when test concepts die inside big companies. But as we know about exponential growth, every step in an exponential function is equal to the accumulation of all of the previous steps combined. So at day 27, almost towards the end of the month, you do finally reach that $1 million threshold, and 3 days later, you've accumulated 10 times what was in that briefcase. This is the counterintuitive function, the way of exponential curves. The way that these curves move is that most of the accumulation of whatever you're accumulating occurs just in the final few steps. It's a really counterintuitive way of thinking about how things develop. And this is critical to making sense of why the world is moving in the way it is. As we've seen, we're seeing more change happen today than we've really seen. In some cases, by some measurements, we're seeing more happen today just in the last 50 years than we've seen in the last 50,000 years. And something like virtual reality, we're seeing more happen just in the last few years than we've seen in the last 20 years. I mean, this is the consistent feature that we're seeing with technology developments. So I'll spend a few minutes on why we're seeing this happen, especially in technology. What's the engine driving this exponential growth? So this might be the most important thing I'll show you today. And if we walk away with one thing, it's remembering what this chart is depicting. So this chart gets at explaining at least some of why we're seeing so much happen. So this is a chart put together by Ray Kurzweil. He's an academic based at MIT. He was also one of the co-founders of Singularity University, where I work. And he asked a really interesting question. So he wanted to know how humanity's capacity to process information, so our computing power, how has it developed over the last 110 years? So I imagine many of us are familiar with Moore's law, the idea that the number of transistors you can fit on an integrated circuit doubles every 18 months or so you get twice as much computing power. That's just in the last 5 decades or so. So keep in mind, 100 years ago, a computer used to be a job for people. There are rooms of what were called calculators. That photo there is a picture of some of the earliest computers. And so what we've seen in the development of computation is this exponential development in its price performance. So price performance, I mean, if you pay $1,000, how much computing power do you receive in return? So 100 years ago, you paid $1,000, you were buying human labor. Today, of course, that's not the case. So there's 2 things about this chart that are significant that I'll point out. The first is, this is on a log chart. So this is not drawn to scale. It's not a linear scale chart, which means that every dot there on a logarithmic function, if you were to draw this on a real piece of paper, this dot on the left is 1,000,000,000 billion times lower than the dot all the way on the right. This chart would be 60,000 times further away than the moon if you drew this on a real piece of paper. I mean, that's the scale of computational development we've seen. Just in the last few decades, if you think about Moore's law, these were numbers put together by Intel. We heard from Intel yesterday, just looking at their own integrated circuits to try and help us conceptualize what we're talking about. So the transistor, the integrated circuit you see on the left, compared to the more recent iCore processors they're developing today, it's a 3,500 times performance gain. They're 90,000 times more energy efficient and 60,000 times cheaper than they were in the 70s. So to help us make sense of those numbers, what if we saw those same performance gains in a car? So again, this was the engineers at Intel put this together. This car today would go 300,000 miles an hour. It would get 2 million miles to the gallon. The car would cost you 4 cents. I mean, that's the scale of progress we've made in computational power. And we do far more with computers than we do with cars. But just to get a sense of the scale of what we've seen happen in the last few decades. Okay, so that's the first thing. The second piece of this, and this might be even more bizarre and mind-bending to think about, is if you follow that chart, you notice something interesting, that it follows a smooth, predictable pattern. Why is that? This is over a century-old depiction of computational development. We've had world wars, we've had recessions, incredible ups and downs in the marketplace, but you don't see that reflected in this chart. The reason there are venture capitalists in Silicon Valley who religiously make their bets on what companies to invest in based on this chart, if you know with some degree of accuracy where computational power will be in 5 years and 10 years, you can start to imagine the types of technologies you can build with that computational power. This is why exponential thinking is so critical. So the question is, why is it so predictable? So this is what Kurzweil spent his time at MIT really trying to understand. And so he comes up with an idea. He wrote this essay 20 years ago to try and answer this question. He calls it the law of accelerating returns. So really, it's a theory of evolution. It's a theory of evolution primarily focused on trying to understand how systems who learn through trial and error experiment over time. I mean, if you think about biology, reproduction, Darwinian evolution is a system of trial and error, learning over time, what types of biology fit in its environment. So basically, to summarize the concept, what the law of accelerating returns says is that as you build new tools that help you experiment faster, you can use those newly developed tools to then build better, faster tools faster. So the performance gains feed on themselves. So you can use today's computers today's much more powerful computers to build the next generation of better, faster computers faster. So that's essentially the concept of why we see these exponential performance gains in information systems. So here's an example, if that was a bit of a complex or clunky definition. So consider about 10 years ago, NASA and Boeing came together they wanted to build a fixed-wing aircraft, the X-48B. So if you think about how this was built through trial and error over time, if you think about what engineers do, is they build a model, take it to a wind tunnel, see if it works, and then iterate from there. So in this world where they have hundreds of engineers, thousands of pen and paper drawings, they can create a mock scale composite of an aircraft, drag that out of their lab, put it in a wind tunnel, and see if it works. In that world, you can run an experiment once every few months. Now contrast that with what they currently do. Today they use what's called computational fluid dynamics. That entire environment has been rendered into computation. So once something becomes an information environment, so what we've seen in computer science, you can essentially accelerate the speed at which you can run experiments. And that's essentially what's happening in the world today. This is why we're seeing so much change happen, is all of these environments are now becoming information systems. We're moving the world from analog to digital. We're putting all of these areas are moving into computational environments. And so that chart I showed you, that exponential increase in performance gains of computing power, is like the engine. That's like the engine driving all of these areas forward as we put them into information-based environments. That's really it. That's why the world is exploding. We have conferences like VRLA. There are VRLA equivalent types of conferences where they're just seeing explosive growth in every one of these fields happening all over the world. So another more plain way of thinking of this, and this is a concept that's being talked about in Silicon Valley quite a bit, is this idea of software eating the world. We're embedding computation into the physical world around us. One way to think about the world is we're putting more and more computers into more and more things. The chairs you're sitting in, if you think about a company like Tesla, Tesla's a car company is the way we traditional categorize it. Tesla doesn't really see themselves as a car company. They make computers. They can run experiments when their cars are built on software in a way that no traditional mechanical engineering-based automotive company could do. My colleague, David Roberts, tells the story. When he went to meet with the Tesla engineers a few years ago, they told a story about the earliest Teslas that came to market had a problem, being that people weren't paying for the cars. That's a problem. So why? So the earliest Teslas, electric cars, when you take your foot off the brake, we're used to cars that will idle forward, that will creep forward in traffic. But electric cars don't have the same mechanics, so they actually just sit there. And so this was frustrating to the earliest Tesla drivers that, they say it's an interesting car, we like it, but we don't like that it just sits in traffic and you have to accelerate and decelerate every time you're in stop-and-go traffic. So to solve the problem, the retail salespeople call their engineers and say, fix this, you can't sell cars like this. What you expect a traditional car company is you have to do a recall. You need to get mechanical engineers to physically change and modify the physical structure of the vehicle. Tesla, they upload some software to the central computer, and then overnight, there's a feature, it was called Creep, that anyone who had a Tesla now has this feature that they could press a button, and now the car behaves like a gas car. That concept of thinking like this car more like a computer, the way we download software updates to our phone, that's coming to the physical world around us. Our clothing. We're going to have a world in which we wake up one day and your jeans have a software update, and they're going to be able to diagnose you with a performance injury because you're walking in a weird way, and then they're able to text your doctor and schedule you a session with your doctor to get checked on. This is the world that's coming. So I want to spend a few minutes just I'm going to talk about two technology examples that are not in virtual reality, just to highlight some of what we're seeing and what we're talking about, this idea of rapid experimentation and information-based world that we're moving into. So the first is 3D printing and robotics. So in 3D printing, so this is a MakerBot. So if you've tracked what's happening in 3D printing, you could think of this as kind of like the Oculus Rift of 3D printers. What I mean by that is it's a technology that took the big, expensive $200,000 machines that only the wealthiest companies and research labs had access to and created a $200 version that consumers could buy. That's essentially what the Oculus Rift did to virtual reality. Today, this doesn't really make anything that people want to pay money for. That's today. But what it did do, what the MakerBot and other consumer 3D printers did do, is it changed the way big companies and manufacturers are thinking about how to make stuff. So one example, which I think is quite fascinating, is Under Armour. So this is a company that makes shoes, they make apparel. They wanted to create a pair of sneakers. I've got a pair of one of the early versions of it. that use the least amount of material as possible while maintaining the highest strength to weight profile. So when you walk around, it still maintains a high strength profile, but uses far less material. So the way they built this is they basically gave those design constraints to a computer. So instead of having a human try and engineer, come up with the ideas, the experimentation that I'm talking about, they gave it to a machine learning algorithm that basically experiments and tests all the possible outcomes of what gives you those design constraints. And then what it comes up with, in this case, is this lattice structure, this weird kind of thing, which, by the way, you can never manufacture this in any other way other than 3D printing. You could never injection mold. You can never create it. You would need only 3D printing allows for the manufacture of this type of interweave complexity. So that changes the way we think about how we might build stuff. So let's think about what that might mean for a business. So think about apparel companies and how they function and how they go about their business. So if you're an apparel company, you probably have on your staff someone whose job it is, which is probably a really fun job, to come up with ideas of what people want to wear. So you have someone who's a designer who thinks about what people are going to be wearing in the fall, and months before you go to market with those clothes, you need to put in an order. Usually, most of the clothing purchased here in North America are manufactured in Asia. The best companies in the world, Nike, Zara, they can come up with an idea and get those onto store shelves in about 9 months, which is a pretty impressive feat considering. But if you're a company like Nike or Zara, you need to do a lot of research in figuring out how many small, mediums, and larges to buy. If you guess high, at the end of a season, you've got warehouses full of clothes, you're doing warehouse clearance sales. If you guess low, you're leaving money on the table. And so it's this imperfect, imprecise concept of trying to guess in 9 months' time what people are going to be paying for. So that's how we currently do things. So contrast that with how software works, what we're talking about using software like the Tesla. So this is a small proof of concept company based in Seattle. One of another speaker at Singularity University, Pablo Holman, who founded it, they make one piece of apparel. They make leggings, the yoga pants, for both men and women. That's the only piece of apparel that they make. So the way that Bombsheller works is they don't have a single designer on their staff. In fact, they rely on a community of designers who can go online. If you have an idea for something, you can basically just upload. In this case, if you like a cool map, you can throw it onto these leggings, and that's what the leggings look like. Then, if you go on their website, they have an entire catalog of leggings that have been designed not by anyone on their staff, but just you and I, the customers. We can go and come up with our own idea. And then, again, unlike other apparel companies, if you want to show someone what this looks like, none of these have ever been made. All of these images are being rendered with basically video game technology, really powerful software to show the customer what the leggings would look like. So then when you as a customer want to go online, you buy it, you click Buy Now, the material in their factory comes off the factory line, gets cut into the size that you need, and then the inkjet printer, basically, it doesn't care what design it prints on, just prints on the design, gets put in a box, and sent to you. There's only one piece of this entire process which is not automated, and that's the stitching. So they have seamstresses on their staff. That's the final piece of this, which is, again, the complexity of stitching is still quite hard and a difficult engineering challenge. So if you go to Bombsheller, that's really what they have and who they have on staff. But again, we're seeing incredible innovations coming in this space that might change how we make and manufacture, in this case, apparel. And so to bring this back to why I talk about 3D printers, a way to think about this, and you're seeing the very sort of early, embryo version of this world we're moving into, what you're looking at is essentially a programmable factory. It doesn't care what you send it, how many of what you send it. It's just going to make what you want. You could send it, a pair of shoes, leggings, a car, a pair of sunglasses, one of them, 100 of them. It doesn't care. This is going to change the way we make stuff, and it's going to change the way we make stuff into more like how we make software. So that's the first one. The second technology that I'll cover just briefly is one that we're seeing an extraordinary amount of development happening just in the last few years. Maybe the one technology that's getting the most amount of press and sort of mainstream coverage, generating discussions. You may be quite fascinated with this as well. I'm curious, how many of you are familiar with deep learning, have heard of these deep learning? Yeah. So for those that haven't, this is essentially what a deep learning neural net looks like. You could think of it as layers of digital neurons. I'm generalizing a bit, but you basically send these digital neurons, huge data sets, and either in a supervised way where you label the data and train these algorithms to understand what it's seeing, or in an unsupervised way where it essentially just finds its own patterns within the data, we're starting to see really interesting applications of this. So the story of AI is fascinating. It's interesting. These are actually very old techniques. Deep learning neural nets have been around for several decades. The reason that we're seeing them now have this resurgence is because of another exponential trend that we're seeing, which is the fall in the price of storing information, storing data. It used to essentially cost the price of a Ferrari to store a gigabyte of information. Today, that's essentially free. It's basically a non-factor. And today, we're just exploding the amount of information we're creating. I mean, anyone walking around with a smartphone is just leaving, gigabytes of data, wherever they go. The planes flying us around the world are creating terabytes of information every single day. The cars we drive, the storefronts we walk in front of. I mean, everything today. This is maybe one of the most explosive exponential curves we're seeing is just the amount of information. So that's really, now that we have the data, these deep learning neural nets are coming online and are having practical use. So I'd like to talk about the Watson project that IBM's developed as a way of describing sort of the state of the art of what we're seeing in AI and machine learning. And I choose IBM's interesting. So every 10 years or so, they create a challenge for themselves in computer science. So 10 years ago, they said, can we build a system that would beat a world grandmaster in chess? So in the 90s, this was at a time where experts were saying there's no way, chess is far too complex, there are far too many permutations in a chess game, it's not going to happen. And then in 1997, they built Deep Blue, which at the time beat Garry Kasparov, a world grandmaster in chess, earned international headlines, worldwide praise, it was a huge deal. So then 10 years later, they said, okay, so chess was interesting, but can we build a system that can navigate something even more complex than chess? And so they chose as their environment natural language. And so we take for granted how complex language is as a system. We learn from a very young age how to communicate verbally, but linguistics as an academic science is incredibly complex. I'll show this clip. This is from Jeopardy from 2011. So this is Watson able to compete with these two individuals on the game show, and you'll get a sense of how a system like Watson was able to navigate this environment.
For 400. Familiarity is said to breed this from the Latin for despise. Watson.
What is contempt?
Correct.
Let's finish magical mastery tour.
In 1939's cartoon The Pointer, this guy got a new, more pear-shaped body, and pupils were added to his eyes. Watson.
Who is Mickey?
Mickey Mouse, yes. Now the last clue. Even a broken one of these on your wall is right twice a day. Watson.
What is clock?
Clock is correct. And with that, you move up to 23,440. 18,000.
Does anyone watch Jeopardy? Does anyone know who this guy is on the left? Ken Jennings, yeah. So Ken Jennings, for those that don't watch, he's this kind of cult icon hero in Jeopardy circles. He set this unbreakable record of consecutive Jeopardy wins. Does anyone know the other person? Does anyone know who Brad is? Wow, can you say that again? He's the all-time champion? You, sir, are the first person I've ever met who has ever known who Brad is. Brad is like the all-time champion, like the second best Jeopardy champion, doesn't have like a cult following. I've never met someone who knew who Brad was, so this is great. Thank you. So these are the two best all-time Jeopardy champions that have ever played the game show. And Watson was able to beat both of their combined scores. Just an unbelievably impressive breakthrough. So let's explore a little bit what actually is taking place when you see a system like Watson. And you may have seen this at the bottom, there was a ticker. So what's been true of computer science and software engineering, and the term engineering is really critical here, is you give a piece of software some input, some piece of data, and it's got its logic gates engineered in a way that it gives you an output. So it's all about input, output, here's the information, and it gives you an answer. So Watson doesn't actually give you an answer. What it's giving you is a probability, and the ticker at the bottom of the screen is giving you the probability of what it believes the answer could be, and the confidence meter is indicating how confident Watson is in its own answer. So it's not giving an output per se. And the really interesting thing about the way Watson was developed is it wasn't engineered in the way that a software engineer might control and engineer the logic gates. It actually self-taught itself based on new information. It was constantly self-correcting. This is where the term machine learning comes from. And developed itself. They actually had to train Watson for about a week before. They didn't just build Watson and then turn it on and let it play Jeopardy. They built the Watson system, and then for about a week trained the algorithm to understand how to navigate these questions. That transition from top-down engineering to this bottom-up self-teaching system, that is maybe one of the most significant things happening in the world today, where we're moving beyond these engineered systems. These self-taught, self-developed systems that are coming online are going to have an incredibly impactful presence in our world. And we're starting to see, the acceleration of this as well. You may have seen last year, Google, their project DeepMind built a system called AlphaGo, which at the time of this announcement was preparing to play the world's best Go champion. So Go, if you're not familiar, it's another information perfect board game, kind of like chess. The difference is the complexity involved. Where chess has an 8x8 grid board, Go has I believe it's 18 or 19 by 18 or 19 grid board. I mean, there's just the way Deep Blue in the 90s played chess was it used what's called brute force computing, where it basically tested every next possible move it could make and then selected the best possible next move. With Go, the complexity of the game is so far beyond what any computer would possibly be able to do that there's no way it could test every move. So it had to develop, the system that played Go had to develop what we might call intuition. The most fascinating aspect of this development is the engineers who built the system, once they've developed it, they actually don't know how it works. They actually don't know how the algorithms have developed themselves. They basically watched it play millions and millions of Go moves, and then once it had a sort of a baseline understanding, had it play itself to reinforce the best possible strategies. And once they've done that, they now have a system that can beat the world grandmaster in Go, but they also have a system that fundamentally they don't know how it works. And these are the types of systems we're now embedding into the physical world. Driverless cars. The first application for Watson was a fascinating use case is in healthcare and medicine. In Japan, there was a patient who was diagnosed with a rare blood disorder, and when the physicians tried to treat her, they were frustrated that she didn't improve her condition. And so they partnered with IBM and basically fed all of her genetic information into the Watson system, read all the latest medical literature, and came up with what at the time was a surprising diagnosis, leukemia. And when the physicians treated her for that, she did improve over time. So we're now living in a world where in medicine, we're doubling the amount of medical knowledge every few years. I mean, that's an exponential curve. No human can possibly keep up with all of the medical knowledge that humanity collectively is creating. We're going to need to rely on these types of machines to help us, in this case with diagnosis. This has incredible implications for what this does to jobs, how the patient-physician relationship. Physicians aren't going away, but the nature of what they do is certainly going to change as a result of this. Maybe the most fascinating application I've seen recently of these types of machine learning, a company in Mountain View called Orbital Insight, they basically get access to satellite imagery. So the amount of images taken of planet Earth is also on one of these exponential curves, just exploding the amount of pixels we're creating of planet Earth. So what this company did is they trained a machine learning algorithm very simply to understand what a parked car in a parking lot looks like. And that's basically it. Then what they were able to do with that information is they can go to any retail store like a Walmart or a Westfield Mall, and by understanding how many parked cars are outside that retail environment, how likely they are to hit their sales numbers. So we're now essentially replacing a room of Bloomberg analysts trying to figure out, sales estimates with a giant eyeball in the sky and a machine learning algorithm that can just tell you, consumer spending habits and how likely we are to hit those numbers. I mean, this is really incredible stuff. So then how good are we? And I'm coming to a close here. How good are we at making sense of these exponential curves? I spoke about at the beginning, intellectually we should choose that penny, but emotionally, how good are we at actually doing this? So in the 80s, if you know the example, so AT&T hired McKinsey to do a study. They wanted to know if they should get into the mobile phone industry, into the mobile phone market. And so they asked McKinsey to do a research study and make a prediction for how many mobile phones would be on the market by the turn of the millennium, so in the year 2000. So McKinsey does their research, and they come back with an answer. They said that by the year 2000, there would be 900,000 units, 900,000 mobile phones in the world. Fast forward to 1999, the year before the turn of the millennium, we were selling not we, but the world collectively were purchasing 900,000 mobile phones every 3 days. I mean, unbelievably beyond what McKinsey had predicted. So what happened? McKinsey got it way wrong. But did they? I mean, if you think about it, so when McKinsey does their research, if you think about what a mobile phone looked like in the 80s, it doesn't look like the devices that we, carry around now, or even in the year 2000, we had those flip phones. This is what a mobile phone looked like. It was a big, heavy briefcase. It was, clunky. You had to charge it, put them in your cars. This is what people used them for. So they weren't wrong. We didn't have 900,000 of these. What they missed was the exponential improvement in the price performance of the components that make up what a smartphone looks like. So one of the challenges with all of these exponential curves is that we don't really even know what the right questions to ask are. A better question might have been, what will a mobile phone look like in the year 2000? And think about how this might apply to virtual reality. We're kind of in this era of VR. We're thinking about projecting forward these, headset devices that we're using. So this is the framework. This is what we're seeing. So that white line, that's us choosing the briefcase with the $1 million. That's how our brains work. This is how our industry forecasts operate. I think John Riccitello from Unity showed a curve very similar to this yesterday. But this is really why technologies die inside big companies. When you make a bet, we see the beginning stages of it, and we're left disappointed. I mean, this is largely what's happened with augmented reality headset devices a few years ago with Google Glass. It's clunky, it's expensive, you look like a cyborg when you wear it, it's not cool. But this is where we're now learning, this insight that most of these technologies are following, especially these information-based systems that are running software and computation, follow this exponential curve. And that's a new insight. This is something that we globally as businesses and politicians collectively are only just beginning to understand. And I think virtual reality is a really iconic example of this. I mean, for 20 years, we've been talking about virtual reality as this next big, technological wonder of the world. Each one of these Wired magazines had a feature story basically arguing in some way or shape that VR was exciting and here and ready for the consumer adoption. But of course, we're only now maybe seeing the beginnings of this. So to return to these two gentlemen, I want to leave you with just a way of thinking about why these stories are becoming more commonplace in the world. And so there's really a few things that happen as a result of these exponential curves. The first thing is that things that were once only available to wealthy research labs, universities, governments, and businesses are becoming available to many more people. And that's because they're becoming cheaper. That's really why that's why VRLA is here, none of the technology here, I mean, it's improved, of course, over time, but a lot of it is essentially the same things we've had for decades. The only difference is the cost. It's cheaper. Secondly, when things become cheaper, you're going to have stories like Palmer Luckey's where single individuals are able to use those tools to do interesting things. And then finally, one thing to think about is we're melting away the physical world with software. So one example. So 10, 15 years ago, if you wanted to measure your brain activity, you would need to go to a research lab that had access to one of these. This is an MRI machine that cost millions of dollars. You would need to go to a clinician's office, and this was how you could measure your brain activity. Contrast that with a device like this. This is an emotive headset. Of course, not nearly as high fidelity. It's not nearly clinical grade, but it does give you a basic understanding of what's happening, at least in your prefrontal cortex, the EEG activity. So a technology that was once only available to clinicians' office, now a consumer device that many more people have access to. This is Will Henshaw. He's a musician. He was in a band called the Eurythmics in the 80s. He wanted to understand how listening to music affects the brain. So using these headset devices that are available as consumer devices, he worked with a team of neuroscientists to see if he could compose music that would put the listener into an alpha state, which in neuroscience is the brain state correlated with being in a state of focus. It's the alert, happy state of focus. I'm curious, how many of you had coffee today? See, okay, so that's a good number of you. So I imagine for a lot of you, this is the brain activity that you're after, this alert, alpha state. So this is a website that he created. It's called Focus at Will. Basically, the idea is you put on it's kind of like Spotify or Pandora. You put on the music, you forget about it, you listen to it, it puts you in an alert state, and you can get work done. Now, if you're Starbucks or Illy Coffee or Red Bull, do you consider a musician working with a $100 headset and a laptop computer building a music service as a competitor to your business? That's a really difficult thing to see coming. You're in the food and beverage industry. The categories we use to describe our world are, in some sense, helpful, but in another sense, limiting. And because we're basically melting away the physical world with software, this is going to have really disruptive and hard to navigate implications. And as we see that with something like virtual reality, this is essentially why virtual reality, one of the reasons it's so exciting, is you can take the physical world and melt it down and democratize experiences, as some of the other speakers have pointed out. So if you think that this is only for gaming and entertainment, I point companies to this example. This is a company called Wessel's Tanks. They're in the industrial pressure tank industry. They used to have a very traditional marketing strategy where they would take one of their tanks, a physical, actual example of one of their demo tanks, to a trade show in Las Vegas once a year. They had a budget for about $500,000 to do this, and whatever customers would come to their trade show, that would be who they would acquire for customers. And then a few years ago, one of their marketing executives hired a firm called Arch Virtual that basically created a VR version of that. And this is a story I imagine many of you in this room are familiar with, the use cases of VR at trade shows and marketing. But think about what this means. You've taken something that was a scarce thing, in this case, the experience of seeing a pressure tank, and you've created an abundant, software-based version of it. You can give, a headset and an Oculus Rift to, dozens of your team members and send them out into the world, and you explode the number of people who can experience, in this case, a pressure tank. So this is really what's happened over the last few decades. Humanity is going through this significant shift in that we're becoming a virtual species. A lot of the things that we used to have physical things, flashlights or GPS devices that were physical objects that you could go to Walmart and take home, and there was a truck that had to deliver them and a factory that had to manufacture them. All of that's now being melted away into software, into lines of code. That's really what's happening to the world around us, and it's been happening for quite some time now. We're now living through a period of time where that's only accelerating, and virtual reality is going to continue this trend. So really, we've come, in the story of science and technology and engineering across the last, few hundred years. This is, we've made changes, we've made progress, we've grown in our tools, but this is really where we're going. And so, as Ray Kurzweil, this is what he looks like, one of our founders, he says, we want to experience 100 years of progress in the 21st century. It'll feel more like 20,000 years. And that's a really difficult thing to understand, but again, that's the counterintuitive nature of exponential growth, and that's really what we're seeing. So with that, I want to thank you. I hope you've had a great conference, and thanks for spending some time here with me. So I think we have time for a couple questions. I'll just signal it's really bright. These lights are really bright, so if I can't see you. I think there's one right here in the front where I can see. Awesome.
Oh. So in thinking about machine learning and AI and its ability to obviously process data and now become predictive, I'm also anticipating that pretty soon it's going to start to be able to understand the language of metaphor as well. Could you speak into a little bit if AI will end up making predictions so accurate that it can't replace any kind of human predictions insofar as it regards to the exponential curve, because it's beyond our ability to predict, as you've pointed out. Won't that then make it sort of the ultimate ruler? I mean, once we trust that its decisions are going to be correct, then it basically can control everything on the planet in a much more efficient way than human decision making can.
Yeah, I think it's a fascinating question. I think it does touch on some philosophical questions about what is considered true, how decisions get made. I'll just signal that. So my answer that I'll give you is largely influenced. My girlfriend, who's a PhD candidate in University of Amsterdam, this is actually what she's researching. So we get into these discussions about this topic quite a bit. Her name is Alex Rubsam, if you want to look at her research papers online. But one of the distinctions about AI that's important to note is that we tend to assume that it's objective, that it's an objective decision-making system. The problem with that thinking is that we tend to forget that AI and machine learning algorithms are only as good as the data that it's being fed. And so data is actually quite a biased thing. We're seeing already systems, AI systems that are just basically absorbing all of the prejudices and cognitive flaws of human reasoning, human thinking, as a result of the data that it's being fed. And so we have to be very mindful. I think this is a really significant thing to keep in mind about AI, because as we deploy these systems into the world and we rely on them to make what you're essentially describing as like giving us objective answers, the truth, so to speak, that is beyond what we as humans, lowly humans would be able to come up with. I think that's flawed in that these AI systems are biased. They're biased and they're just absorbing our own biases, and our own biases are, understanding are biased in that the data sets we create are data sets of things that we deem significant or relevant, and through all of human history, what we deem significant and relevant changes and fluctuates. And so I think it's a really dangerous thing to think about giving objective reasoning, decision-making agency to these machine learning systems. I don't believe that we will have these AI overlord rulers in the sense that many like Elon Musk is talking about. But they will surprise us. I think the idea that AI systems behave in ways that we don't really understand, we won't be able to ask an algorithm, hey, why did you come up with that decision? We won't be able to understand perfectly what's happening inside of them. So it'll become like a partnership, and I think that's important to keep in mind.
Well, that's what I was sort of pointing towards its ability to make predictions and run scenarios out into the future so much better than we can that we'll start to trust on it, even though it may not be making the actual decisions, but in terms of, and I'm talking about more political policy type stuff, environmental and resource distribution and stuff like that. When it's finally, most of the time, it's right, and it becomes prudent to follow that advice, what then?
So that's a great point. And I think what's in your question is really insightful is when they demonstrate consistently, like something like in healthcare, honestly, I do believe something like that will happen in healthcare, where it'll just become barbaric to hand over a diagnosis, the task of diagnosing something to a human physician. It'll become like GPS. This is another metaphor my colleague David Roberts talks about. Is what's that?
Like compared to getting directions from somebody on the corner, right?
Exactly. So this will happen, but again, they won't be perfect. The thing is that these AI systems, the reason they're coming up with the answers they do is because of the data that they're being fed. And so I don't know. I don't know how we'll be able to maintain this ability for questioning and doubt, but you're right to point out that in certain environments, we have to be mindful of the agency we're handing over to these systems. But things like driving cars, making medical decisions, there are things that AIs are going to be better at humans, and we will, of course, be handing over that decision-making process to them. How society functions in that world, that's what we're going to have to deal with.
Peel back the layers of reality. Another topic of conversation that's come up recently is the idea that we're living in a simulated reality, so to speak. What are your thoughts on that? And do you believe that's a valid kind of question to ask, that we're living in a computer-generated reality?
That's a great. I think it's a fascinating topic. So there's a great New Yorker article that points out there's two premises that you have to buy in. I know we're out of time, so I'll just address. There's two premises that you have to buy into to believe that argument, and then and then on the flip side, I'll share a theory which I'm fascinated by, and it touches on VR. The premise that we're living in a simulated world comes down to that conscious experience is a product of information processing. And this kind of aligns with this concept of that the human brain is a computer. Again, my girlfriend speaks about this and does research. She's a cultural analysis PhD candidate that looks at the way humans have described our reality and existence has, for all of human history, just modeled whatever the latest technology was of its time. So, in the 2,000 years ago, hydraulic systems, aqueducts, the human consciousness was a product of, fluids moving about. It was like hydraulic pumps. A couple hundred years ago, with the rise of machinery, industrial revolution, human experience, the human brain was a product was sort of like a mechanized system of levers and pulleys. Today, the dominant metaphor to describe human experience is information processing, is computers. I'm not saying it's not, but we just it does seem to model this pattern of human behavior of making sense of reality based on what the latest thing is. So one, you have to believe that human consciousness and the brain is just, inputs and outputs, information processing system. And the second premise is, I'm blanking on, but so there's a New Yorker article that looks into this. On the other hand, there's a theory that I find really fascinating by someone who actually spoke at VRLA last year. His name's John Smart. I don't know if anyone was here last year. He was one of the speakers. And so he looks at, and I think this is a fascinating concept. So he has this idea called the transcension hypothesis. And the theory aims to address a question of Fermi's paradox. If you know what Fermi's paradox is this question: if we look out into the cosmos and we're learning more and more about the solar system, the universe, and the design of the universe, as the more we discover, the more we're finding how well designed it is to support life it could. We're just discovering trillions of exoplanets orbiting, star systems in the habitable zone that, if it had, chemistry and water, could theoretically support life. So the universe is designed, it seems, to just be this life-spawning thing. The problem is we see no evidence. There's no blinking lights. There's no technologically advanced Star Trek-like world out there. And why is that? I mean, mathematically, it's an impossible concept that we, would be the most advanced technological species. So John Smart is a futurist, comes up with this idea. It's called the transcension hypothesis, which basically says that as any technologically advanced species develops over time, is that they don't colonize outer space, something that a young technologically growing species would do. If you see what we're doing, we're throwing bottling up Earth and putting our bodies into it and sending ourselves to weird parts of our near solar system. We actually colonize inner space. We go inner. We see computers that were once the size of buildings. Now they're the size of our fit in our pockets, and that will continue to compress so that we can house really complex universe scale realities on computation that's contained in infinitely small environments. And so the reason we don't see evidence of any technologically advanced species is they don't colonize outer space, they basically move into virtual reality. And then if you think about that, then there's no reason why we're not already there. So I think that is actually a really fascinating way to model what's happening in the world today. Flashlights that were physical things are now lines of code. The graphic that you saw at the end. I think it's a helpful framework, but do I actually think that we're in a simulation? I mean, this is the oldest question that humans have been trying to figure out is, where did we come from? Why are we here? Is there a creator? And if so, what is the nature of that creation? And the simulation theory it's a creation myth. And it's a story, and it's an interesting one. Could be true, it could not be. But I think it models our current era in time, and one that is largely driven by this computational age that we're living in. So, yeah. I think with that, I'm being yanked off stage, so thanks.